Hey class, this is going to be your 5.3 lecture. So we got to start with a definition, and the definition can be a little involved. That's why I wanted to write it down first. I've actually written it out a little bit differently than the way it was written in your book, so you can compare the two and see what's the same and what's different, and kind of get a feel for it that way. So this ties into the idea from last time of those finite sums. So what we're going to do is we're going to set up a particular partition of our interval, and that partition here is going to be, have n points in it. It's going to have a left endpoint, a right endpoint, and a bunch of other points in the middle. And your book goes into the delta and epsilon here, and this is one of the places where I'm skipping. The idea here is as n gets larger, this partition needs to have its maximum distance between points shrinking to 0. So we're not just piling a bunch of them up, here's A, here's B, and we're not just piling a bunch of points up over here and leaving half the interval uncovered. We have to be adding them in. Each time I add a point, I want to be making this distance between, the maximal distance between points, smaller. Truthfully, we're going to do this in our class. Like I said last time, we're going to use even intervals. So we're going to evenly space our x0 to xn. It's the easiest way we have to guarantee that that norm of the partition goes to 0. And every choice of point in each of those intervals in your partition. So this limit needs to not just work for one, it has to work for all of them. There's actually an example in this section of a sum that goes to different values depending on how you choose some of these things to show you how this could break. Remember, delta xk is just the width of each interval, so the width of this interval would be delta xk. Again, for us, this is usually going to be the same number every time because we're going to evenly space our intervals. So ck can be any point in here, and when we do these sums, we typically take it to be a left or a right endpoint because that makes our lives simpler, but only if we already know that the limit exists. And so the limit has to exist and be equal. That should just be an equal sign, not an arrow. The limit has to exist and be equal to the same number for every choice that we made up here. So this j needs to be the same no matter if I decide, no, I don't want x2 to be that. I want x2 to be something else. It still needs to have this limit. If so, then that number is the definite integral of f over ab. And instead of writing this Riemann sum notation every time, we can use this notation. So this is the integral from a to b of f of x dx. That's how we read that, the integral from a to b of f of x dx. And so remember that a specific choice of this was modeling what happened between a and b, right? If we, here's a 4 rectangle choice with, let's take left endpoints just because they're easy to draw here. So then that would be like what we did in 5.2, but now what we're saying is, well, but let's keep letting these number of rectangles get to be more and more and more, so that the width of each rectangle, that's the width of the widest rectangle, is going to 0. That's what this symbol means. That's the width of the widest rectangle. We call that the norm of the partition, but nobody's going to say that again to you until Calc 3. So the limit as the number of rectangles goes to infinity in such a way that the width of all the rectangles is going to 0 will be equal to the definite integral from a to b of f of x dx, which will be equal to j, which is that common limit. So a couple of little terminology points. So if the integral from a to b of f of x dx exists, then f is said to be integrable on a b. And while I'm at it, we typically talk about if f is continuous or piecewise continuous with only finite jump discontinuities. Then f is integrable. So most of the functions that we have ever talked about are going to be integrable. So any continuous function, that limit's going to exist. If it's not continuous, sorry, I'll just do that one again, down lower. If it's not continuous, but I only have so many jump discontinuities, then I can still find this value, and the trick's going to be, I'm going to go ahead and we're going to get this in a few minutes, but the trick here is to just split it up into intervals which are continuous, and then we're going to be able to recombine our intervals. That initial formula is pretty annoying and not one that anybody likes to use. So let's talk about equal width subintervals. So we're going to start with interval AB, and we're going to divide this into n equal subintervals. So each will have a width, delta x will be equal to b minus a over n, right? And we can, let's talk about right endpoints. And I think we did this last time, but it's worth repeating. So the right endpoints, so the first one would be a plus 1 delta x, and then a plus 2 delta x, and then so on until we finally got b. And the formula for that is we'd say ck is equal to a plus k times delta x. When k is n, that's going to be a plus b minus a, so that's just going to be b. And when k is 1, that's going to be a plus delta x, which is my first right endpoint. And so you can see why that would work. Our book likes to write this as a plus k times b minus a over n. They don't like to call it delta x there. I do, but then once you're actually evaluating it, you do want to switch back in, so it's probably the same either way. So in that case, we can say, so long as this limit's going to exist, the integral from a to b of f of x dx will be equal to the limit as n goes to infinity, the sum k goes from 1 to n of f with ck plugged in. I'm going to write this both ways here, right? Times delta x, which we can then write as the limit as n goes to infinity, the sums k goes from 1 to n, f with, now ck is a plus k times b minus a over n, and delta x is b minus a over n. Now that might not look better, but it's actually easier because we know what all of these things are. So let's do a quick example here. I'm going to actually jump out of order from the book. I've been following along with the book, but I'm going to jump out of order here. So if I do the integral from 0 to 2 of x dx, let's look at, hang on a second. So the integral from 0 to 2 of x dx is going to be equal to, let's draw this out here. So we'll make that 2. So f of x is just x, that's nice. So a is 0, b is 2. We don't get to pick n this time because we're going to take the limit as n goes to infinity. But ck then is just going to be equal to 2 minus 0 over n is my delta x. I guess. But a is 0, so that's just 2 over n. And my delta x is also 2 over n. So, sorry about that. Let's see, what was I saying? So the integral from 0 to 2 of x dx, we need to start plugging in from our formula up here. So we have the limit as n goes to infinity, the sum as k goes from 1 to n. My f of 2 over n is just going to be 2 over n, right? Because it's just x, and so that's just going to be replaced with ck. And then my delta x is just going to be 2 over n. So this is the limit as n goes to infinity, the sum as k goes from 1 to n of 4 over n squared. I skipped something here. ck here is not 2 over n, it's 2k over n. There we go, that's a little better. 2k over n. So I have 4 over n squared times k. The 4 over n squared can come out, not of the limit, but of the sum. So the limit as n goes to infinity of 4 over n squared, the sum as k goes from 1 to n of k. So that's equal to the limit as n goes to infinity of 4 over n squared. The sum as k goes from 1 to n of k is n times n plus 1 over 2. So this is the limit as n goes to infinity of 2n squared plus n over n squared. And that is going to be equal to 2. Right? That's just all there is to it there. Double checking because it was a triangle. 1/2 the base is 1 times the height is 2. So that is what we should have gotten because the definite integral will represent area so long as everything is nice, the area under the curve. We talked about that. So if f looks like this, basically if it's above your x-axis, then the area here is the integral from a to b of f of x dx. But in order for this to work, f has to be above the x-axis, because if it dips below the x-axis, we're going to get some negative area that'll cancel out some of our other area. All right. Let's see what happens when it doesn't work. So if f of x equals 1 or 0, 1 if x is rational, and 0 if x is irrational, then we can pick our same partition here on the interval 0 to 1. And so we'll let our partition be equally spaced here, so this will have delta x equal to be 1 over n, and we'll have our right endpoints of our intervals will be our ck, no, I'm sorry, our right endpoints will be xk, and that'll be equal to k over n, but in between each of these numbers, so for number 1, we're going to do this two ways. We're going to pick ck to be a rational between xk minus 1 and xk. Now, you may not recall this. I'm sure we've talked about, not us, but I'm sure somewhere along the line you've heard this, but between any two numbers there is a rational number, and between any two numbers there is an irrational number. So no matter what xk minus 1 and xk are, we can find a rational number between them. But in this case, f of ck is always 1, and so the limit, or I can just say f of ck times delta x summed as k goes from 1 to n is always going to be 1. We'll have a height 1, and we'll have a total width of our intervals of 1. And so the limit of that as which is going to then approach 1 as n goes to infinity. Oop, off the screen. So this will, 1 approaches 1 as n goes to infinity. But then the second way, we can underestimate our area by picking ck to be irrational. There's always an irrational between xk minus 1 and xk, so then in this case f of ck will be 0, and so our limit will be 0. And this is an example of where you have a function that isn't integrable, because depending on the choice, in this case of ck, how we picked our ck, we get different values for the limit. So it's not that the limit necessarily has to not exist in order for it to not be integrable. That's another way it could happen, but it could exist and just be equal to different things based on choices that we made, in which case it is not integrable. But this is probably the weirdest function you've ever dealt with in a math class. That function is not a normal function that we deal with. So any of the normal polynomial functions, rational functions, trig functions, so long as our intervals are finite, right? A trig function has lots of discontinuities, but they're spread out. So if you have a finite interval, it's going to have a finite number of discontinuities. Now those are infinite discontinuities, which can be troubling in some cases, so not always. But we have quite a lot that we can do. What else? Root functions, exponential, log functions, all of these should be integrable at least on some intervals. This function is not integrable on any interval. We have some more we have some properties. So you can read along off of page 321 if you want, but if f and g are integrable on AB, then so this first one is actually pretty neat. The integral from b up to a of f of x is equal to the opposite of the integral from a up to b of f of x dx. And the reason why this is so is if I assume a is less than b, like I've written here, then if I integrate from b to a, then every time I take my delta x, I'll get a negative number. And so I'll get like a negative width. That's one way to look at it. But this is a super useful property. We use it all the time in calculus. So sometimes taking the integral in one direction is not convenient, so we can just take the opposite and take the integral in the other direction. Number 2. If I integrate from a to a, any integrable function, I get 0. This interval has 0 width. F, if it's integrable, has to have finite height, so it's like a rectangle with a height and no width, and so that's 0. 3 and 4 come just as properties of the limit and the sum, so the integral of a constant times my function is equal to the constant times the integral of my function. So we've seen that when we did limits, we've seen it when we did derivatives, we saw it just earlier in chapter 5 when we did sums. This is part of the integral being a linear operator. And the other part of that is that the integral from a to b of f of x plus g of x dx is equal to the integral of f of x dx, plus the integral of g of x dx. And it's the same if we subtract. Property 5, this is the slick property that I was telling you about that allows us to account for a discontinuity so long as it's not a really weird one. So the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. And so if you think of that as that area calculation, I think you'll see why that's so. But also we can do it from the limit of the Riemann sum there. We could, same thing, right? We have a Riemann sum in here, we have a Riemann sum in there, but that's just one choice of partition between A and C, so that would still work. Let's see, 6. If f has a max and min on AB, then the minimum value of f times b minus a is less than or equal to the integral from a to b of f of x dx, and that's less than or equal to, the maximum value of f times b minus a. And this one is pretty straightforward, but the easiest way to just show you this one is with the picture on page 322. So let me show you that one here. These are each neat pictures, and you should check them out for explanation of the others. But here you have an f that's between its maximum and minimum value. And so the first thing, the minimum value of f times b minus a, is the area of the green rectangle. The outside thing is the maximum value of f times b minus a is the area of the big rectangle. So of course the area under that curve is going to be somewhere in between those. And there's one more property, which is really related to this one. But if f of x is greater than or equal to g of x on AB, then the integral over AB of f of x will be greater than the integral over AB of g of x. So again, not surprising, and that's another one that's worth looking at the picture for, because then it's just obvious. Then it's this picture here. So if f of x is bigger than g of x, then of course it's got more area under it. And even if g of x or some of them dip under, the inequality still holds. So I'm going to do example 2 on page 323, and we start with just the knowledge that we have these values. So we have some function whose integral from -1 to 1 is 5. We have the same function, the integral from 1 to 4 is -2. And we have a different function, and the integral from -1 to 1 of that function is 7. So then we're asked to find the integral from 4 to 1 of f of x dx. That's just the opposite of the integral from 1 to 4 of f of x dx, which is the opposite of -2, which is 2. We're asked to find the integral from -1 to 1 of 2 f of x plus 3 h of x, and that is going to be equal to 2 times the integral from -1 to 1 of f of x plus dx, dx's are important, plus 3 times the integral from -1 to 1 h of x dx. I said they're important, and it's kind of hard to explain exactly why. There's a handful of things. They're telling us which variable we're taking the integral with respect to. That won't really come up very much until you get into Calc 3. They also serve as sort of the bookend for the integral, so we know when to stop integrating. Those are the two most obvious reasons that they're important, and so we'll stick with those for now. So this is going to be 2 times that integral was given as 5, plus 3 times that integral was given as 7, so that's 10 plus 21 is 31. And then finally, what if we're asked to find the integral from -1 to 4 of f of x dx? Well, that's the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. Those values were both given. So this one is 5 plus -2, so the total integral is 3. And so remember what I said, if an integral dips below the x-axis like that, that's how it ends up with, sorry, if the function dips below the x-axis, that's how you end up with a negative integral. So we'd have some certain positive area up here, we'd have some certain negative area up here, down here, but this is bigger than that, so that's how you could get something like a -2. I keep saying it's so, but it is true that if f is non-negative and integrable, then the integral from a to b of f of x dx is the area under f between a and b. I don't think our book does this. The book that they use at the university talks about it being this integral is always a net area, even if f is sometimes negative. So by net area, they just mean positive area minus the area above the curve, area above the x-axis minus the area below. If I think of that as a positive number, that would be my integral. That's the net area. So we can get by if it's not non-negative. All right, a couple minutes ago I did the integral from 0 to 2 of x dx. But what if we did the integral from 0 to b of x dx? What does that change for us? Well, not a ton. Delta x is b over n. ck, if we do right endpoints, is going to be kb over n. And f of ck is going to be ck because that's what we have there. So then this is the limit as n goes to infinity of the sum as k goes from 1 to n of kb over n times b over n. So the main difference here is we get b squared over n squared instead of 4 over n squared. And then that's going to be times n plus 1 over 2. We still have to take the limit as n goes to infinity. But then that's going to be equal to b squared over 2. So before b was 2 and it was 4 squared over 2, and that's how we got it. So that's the definite integral from 0 to b of x dx. Let's go ahead and talk about the integral from a to b of x dx. And for this we're going to use a property, a couple of them. We're going to say this is the integral from a to 0 of x dx plus the integral from 0 to b of x dx. And this is the integral from 0 up to a of x dx, but I've got to make it negative, plus the integral from 0 to b of x dx. This is negative a squared over 2 plus b squared over 2, or we can just write this as b squared minus a squared over 2. We can do those kind of calculations for other things, and this would be a good chance to test yourself out. It's probably going to come up in the homework if you don't do it here, but you might pause and see if you can demonstrate for yourself why the integral of c from a to b dx is equal to c times b minus a. Try to set up a Riemann sum like we've been doing. And then if you really want to challenge yourself, this one relies on one of the formulas like we had last time, it's the other one, n times n plus 1 times 2n plus 1 over 6. So if you remember that one, so this will be the integral of x squared dx over ab. and it's going to be b cubed minus a cubed over 3, so long as a is less than b. What else do we have here? So if I've got a function like so, and I want to know the average value of the function, well, that's the same as the height of the rectangle that has the same area as that function. So the average value of a function is equal to 1 over b minus a, that's the width of the rectangle, divided by the width, I'm saying, times the integral from a to b of f of x dx. So we would calculate the area under the curve, net area if necessary, and then we would divide by the width of the interval to figure out what the height of that average function was. All right, that's it for 5.3.